All right, good morning or good afternoon, depending on where you're joining us from today. My name is Anthony Fasano from the Engineering Management Institute. I'm happy to have with me Matthew Neerman today from Schnabel. Schnabel is a sponsor of the Engineering Management Institute. They've sponsored this webinar, which is a PDH webinar for you. And they want to give you education around this interesting topic and also allow you to get a PDH. So we're grateful for Schnabel today and grateful to have Matt with us. Matt has been with us in the past. He's been a guest on our geotechnical engineering podcast with Jared Green, which was a very well-received episode. Matt joined Schnabel in 1998 as a research engineer. He's a licensed professional engineer. He's currently the vice president of R&D and equipment for the company. His dual responsibilities include managing the research and development and improved design and construction methods, as well as overall management of Schnabel's specialized equipment fleet. And of course, today you're going to learn a lot about soil mix pier underpinning, which is a new method of underpinning structures that increases worker safety and productivity. And Matt's got a lot of awesome examples and images throughout to kind of really show you what it looks like. So with that, I'm not going to waste any more time. I'm going to hand it over to Matt.
Okay, thank you, Anthony. Appreciate the introduction, and I'm glad to be here with you all. So today you're going to learn a little bit about underpinning in general, but the main focus is going to be on this new technology, soil mix pier underpinning, that we introduced a few years ago. So a few learning objectives for you, since this is a webinar for PDHs. I want you to understand what underpinning is, why we perform it. We're going to talk about this innovation to create this soil mix pier underpinning out of four pre-existing technologies. We're going to go over some design of soil mix pier underpinning, and we're also going to be talking about some QA/QC measures for the installation. Getting into a little bit more detail here with our outline, we're going to start out, for those of you that are not familiar with underpinning, going to try to give you a good explanation of what underpinning is and describe the hand dug pier method. We've got a lot of photos for you to take a look at. We'll sort of get into the need for a new underpinning technology and then really focus on the development of this new technology, soil mix pier underpinning. We're going to go over the steps of the installation, take a look at the design, give the QA/QC recommendations, and then introduce three projects for you to take a look at where we've used soil mix pier underpinning. Okay, so what's underpinning? Simply put, underpinning extends the foundation of an existing structure to a deeper stratum. So there's really, two cases when we do underpinning. First is if you have an existing foundation with insufficient capacity. So that's this photo here on the left. We have an existing footing, an existing spread footing. There was going to be some additional load put on this footing. Did not have enough bearing capacity. And so this was an example of some micropile underpinning to increase the capacity of this footing. The other application for underpinning is if you have an existing foundation that's going to get undermined by an adjacent excavation. So this is the photo on the right. You can see this old brick building, and then obviously there was an excavation next to it. And you can see this concrete underpinning that was put in place, basically extending the foundation of the structure from this elevation down to here. So those are two examples of when underpinning is useful and why we might use underpinning. So there are several challenges associated with underpinning. The first challenge that I want to talk about is just this idea of mating the new construction with old construction. It's always difficult working around old structures. You might not know what you have. You might not know the condition of the footing, depth of footing, things like that. So there's always challenges trying to figure out what exactly you have. There's also the issue of we're oftentimes working along property lines. So especially the case for an adjacent excavation, you can see right here, this property line is basically right along this building. The new building is coming in, and we had to install underpinning underneath the structure. Worker safety is paramount. You can't just wish these things in place. You have to design it so that it can be built safely. We're going to talk a lot about that today. Another challenge with underpinning is that almost any time you do work next to or under a foundation, you're temporarily lowering your bearing capacity before you're able to increase it. So you have to be aware of that temporary case. And then the fifth challenge is just that concept, as obvious as it might sound, but the full weight of the structure is generally already in place while we're doing the underpinning. And that's opposite the way normal foundation construction happens. Normally, we're building the foundations and then building the structure on top of those foundations. Underpinning is sort of the opposite. The building's already there, and we're trying to improve or enhance the foundation beneath it. So I want to take you through a really brief example that I think is a neat example from history. So this is the Washington Monument. You can sort of maybe recognize it there on the left. So construction was started for the monument in 1848. And they had two problems. So one is they ran out of money shortly after they started. And the second is there was a little thing called the Civil War, which happened. So that disrupted the construction for about a 30-year period. And you can see here the photo on the left. This is as far as they got before they ran out of money. And it sat like that for about 30 years during the Civil War. So when the new project team came on board, they took a look at the foundations and decided that these were maybe weren't comfortable with the existing foundation. And so they embarked on an underpinning project to increase the bearing capacity of this foundation. So you can see the work here on the right. They're starting to tear into this existing stone foundation. They've got some formwork in place. Here's a cross section that shows what they were doing. You can see they've removed some of the original foundation. They've added a lot of concrete to it. They've gone out wider and deeper. And that's the finished underpinning over there on the right. So really some substantial improvements to the foundations. And then of course, it's worked out pretty well. So there's the monument today. So we're going to dig into this concrete pier underpinning a little more and focus on that. That was a technology that was used for the Washington Monument. And it is the underpinning technology that I'm going to really compare and contrast with the Soil Mix Pier underpinning method. So a picture's worth 1,000 words. I'm going to show you a lot of photos, and then we'll take a look at a typical cross section. So here you can see a foundation wall that's getting underpinned. You can see the beginnings of the hand dug pier operation. They've got an approach pit dug here, and we've started to go underneath the foundation. And you can see we have this wooden formwork around the excavation, and we also have this frame right here in front of the building. And you'll see the reason for that frame here shortly. Here's another look inside the pier. You can see we've gone down, and now we're going underneath the foundation, getting underneath that existing wall in order to extend the foundation. That's a view looking inside the pit. So these are hand dug pits. So there's a worker inside of that pit there. This particular pit measures about 3 foot by 5 foot. You can see the ring boards that are put in to support the excavation to support it as they go down. And we're literally throwing soil and rock into this bucket, and there's a helper on top that's pulling it out. This is a really, really old technology. Here's a few more photos. You can see this worker on the left. This is the person who stays up top. He's assisting the person down in the bottom of the pit. You've got a variety of safety devices that are attached to this frame for fall protection and retrieval. And this photo right here was taken very close to this tower, if not underneath this tower. So you can see over here, this is what we're creating. We're creating these massive concrete piers that extend beneath the foundation. And you can see the formwork outline of these boards right here. That's what you're looking at in this photo here. These are the ring boards, and they leave that sort of pattern going down. So you can get a sense of how deep this underpinning went. Each of those boards is accounts for about 12 inches. This is the same project, just several months later, and backing up a little bit, you can get a sense of the scale of the underpinning. So these are the piers right here that were installed to hold up that building. Obviously, the bearing level is being taken down all around this building. These photos give you another sense of the scale. The pretty substantial tower, stone tower sitting on top of the underpinning. And overall, it's a very heavy building here sitting on top of the underpinning. So this is really hand dug piers, sort of showing what they can do, taking them to a really deep depth and carrying a really high building loads. I'm going to show you, these are a couple other projects with hand dug piers. This is sort of the other end of the depth spectrum. These are fairly shallow underpinning piers. You can see here, though, the application was extending the bearing wall for these masonry structures. It's a stone, sort of a stone rubble type of a foundation. And we've gone underneath and installed these piers beneath it. And, we're only taking it here about 6 feet or so, 6 or 7 feet, perhaps on the right-hand side. And these piers are providing continuous support. You can see they're right next to each other. So all of these stones are supported by the piers. Yep, if anybody has questions, they can drop them into the chat, I would say.
Yeah, I saw that there was a hand raised. Donald, did you have a question that you want to ask Matt? Okay, maybe not.
Okay, no worries. We'll
Go ahead,
keep
Matt.
going. Yep. Okay, here's that cross section I promised you. What you're seeing here is the approach pit on the right-hand side. So we're using the approach pit to get down underneath the foundation. And then once we get down some distance here, we're moving horizontally, getting underneath the existing foundation. We're putting in these ring boards along the side to support the pier excavation. Once we get down to the bottom of the pier elevation, we're filling up this pit with concrete. And we're filling it up to within a couple inches of the bottom of the footing. And then we're filling that gap usually the next day with a material called dry pack, which is a very dry mortar that's rammed into place that provides really good bearing contact between the existing foundation and the underpinning element. And you can see here this cross section shows an accommodation made for some sort of lateral support, like a tieback or a sole nail, if needed, to provide stability for the pier. Because in this case, this section is showing an underpinning pier used for underpinning a building adjacent to a future excavation. You can see the future grade is indicated there. So as you all see those photos and that cross section, you can see that with the hand dug piers, we're creating some really massive concrete elements. Like I said, typical dimensions are in the neighborhood of 3 foot by 5 feet. It's very difficult, if not impossible, to get rebar into these piers. So the concrete is normally designed as unreinforced concrete. I think you could see from the photos that oftentimes the hand dug piers are installed adjacent to the property line. So that's what we call wall line underpinning or wall line shoring. We're using concrete. Everyone's very familiar with concrete, obviously. As we look at the geotechnical design of the hand dug pier, we're typically designing the piers as either a gravity retaining wall or an externally supported retaining wall if we determine that we need additional lateral support. Or you might also be designing the piers as simply a deep foundation or a footing element, and that would be the case of no excavation adjacent to the footing. I showed you an example from Washington, D.C., the monument there, 1848. Okay, so that's over a century ago. Hand dug piers were installed, even well before that. So these have been around a long, long time, but there is significant manual labor involved. And we do have a question here about underpinning rubble foundations, and that's a great question. I'm actually going to get into that here on the next couple slides. So just bear with me, and we're going to get into that. The question is about what steps are taken to prevent existing footing from collapsing into the pit. We're going to talk about that specifically. Okay, so as we look at all that manual labor, I want to put that in context to where we are today. Things have changed a whole lot with regards to safety. And I don't think anyone will dispute that there is a tremendous emphasis on safety in the construction industry. This is some statistics from the National Safety Council. You can see here that there's tremendous amount of costs in 2021 from worker injury. There's also a tremendous amount of days lost due to work-related injuries. And these aren't just numbers. There's obviously real people behind all these numbers. So this is of utmost importance. And things have changed. Construction companies are much more prioritize safety much more than they did in the past. Cultures are improving, and really companies are doing everything they can to attract and retain employees. And a big part of that is giving them a safe place to work. So as we look at hand dug piers, the safety considerations we have, so we just saw that there's significant amounts of manual labor involved in them. More specifically, underpinning piers represent a confined space. So with regards to confined space, you need to monitor and test your air quality, and you also have to have a retrieval mechanism in place for the employees that are working inside the pit. There's also the obvious need for fall protection once we get beyond 6 foot deep. This is for anybody in or outside or adjacent to the pit. And then there's also some overhead hazards, and this gets to Russell's question about the underpinning next to rubble foundations. So the overhead hazards are, of course, we're lifting soil and rock out of the pit. We're lowering objects into the pit, tool and materials. But we also have this consideration about the existing foundations, and they may or may not be stable. So here's a photo I showed you a few minutes ago. Just wanted to point out some of the safety measures we have in place. So you can see the ventilation system right here. We're blowing air into the pier. We're using fall protection. You can see this worker has his fall protection on. He's hooked up to his harness. We have a retrieval device here for any employee that goes into the pit. We have to have a retrieval device connected to them so that if something were to happen, we can pull them out. And the other safety measure I want to point out is roof support. When I say roof support, I'm referring to the roof of the pit. And that is this right here is what you see as roof support. I want to focus on that for a minute. In my opinion, roof support is the most difficult safety measure to install when doing hand dug piers. And the reason it's difficult is because every foundation is different. It's different than, say, fall protection or air monitoring. Those issues are addressed in a standardized way. It's difficult to address roof support in a standardized way. There's a lot of techniques and methods out there, but the bottom line is every foundation is different. Some foundations are going to be less stable than others, and this support has to be in place before the workers are in a position where they could be injured from a portion of the foundation coming loose. So you can see here a typical approach is to get these supports in to hold up these stones. But as we know in geotechnical engineering, you can't wish things in place. So there has to be a certain amount of excavation that happens before these supports can be put into place. And that during that time is when the hazard really exists for the workers. So I'm going to use that to segue into the development of this new technology that we have called Soil Mix Pier Underpinning. And this technology was developed specifically to replace hand dug piers. So that's why I spent so much time showing you photos of hand dug piers and explaining the construction. The primary motivation that we had for developing this technology was safety. The secondary motivations for this technology are schedule, cost, and performance. But primarily, this technique was developed to increase worker safety. And this is sort of a truth for any sort of innovation that occurs. A lot of innovations out there, most innovations, all innovations, are not entirely new. They're oftentimes the product of combining multiple existing technologies into a new product. And that's what we have today. This is Soil Mix Pier Underpinning is really a story of innovation, and it's about combining several pre-existing technologies into a new product for us. And those technologies, you can see them here, are hand dug piers, soil mixing, jet grouting, and rock and concrete grinding. So we're going to spend some time now describing those existing geotechnologies and showing you how we took portions of those technologies and combined them to make this soil mix pier underpinning. So there were some specific attributes that we borrowed from each of these technologies. We're going to start out with hand dug piers. Hand dug piers, the things we like about hand dug piers is we like the fact that they're rectangles. So for engineers, that makes them easy to design and draw. We like that they have known dimensions. We like the fact that we are dry packing to the footing to provide really firm contact between the footing and the foundation element. And we also like the fact that we can install hand dug piers a wall line. So that's an important characteristic of hand dug piers. This on the left is that cross section I showed you earlier. You can see the hand dug pier here. On the right, you have the product that results from Soil Mix Pier Underpinning. So we're going to get more into this, but you can see we are creating this block right here of soil cement. And there's some similarities here with the hand dug piers. So you can see that we're achieving rectangular geometry, at least in the section view. We can do the same thing on a plan view. Install a rectangular square or rectangular pier. We know the dimensions. We know how far back we're going and how deep we're going. So we know the dimensions just like we do with hand dug piers. We can dry pack our soil cement pier to the footing. So we can leave the soil cement low and fill this gap here with soil cement. And we also like the fact that we can install these as a wall line. So this dotted red line here shows you a typical wall line next to a footing. We can do the same thing here with the soil cement. We can remove all of this material right here and provide the owner or contractor with a wall line underpinning solution. Question here about depth limitation. Yes, there is a depth limitation. It's really a practical limit that's based on the equipment. So it has to do with the size of the equipment that we use, the size of the cutting tool, and the size of the excavator machines that we use for soil mix pier underpinning. Typically for installing Soil Mix Pier underpinning, if we're talking about a single pass, we can approach about 15-foot depth for the Soil Mix piers. Once we go beneath that depth, then we're looking at either putting in additional tiers of Soil Mix piers, or we're supplementing the Soil Mix piers with another underpinning technology to go deeper. For example, we could use hand dug piers or micro piles or bracket piles or something like that. I want to jump over to the next existing technology that we borrowed from, and that's soil mixing. And from soil mixing, we're borrowing what we know about soil cement mix design, and we're also borrowing what we know about mechanical mixing. So let me get into that a little more here. So soil mixing, if you're not familiar with soil mixing, that's where we take a cementitious grout and we're mechanically mixing it with the soil to create a soil cement material. This is commonly done with drilling rigs. We're installing cylindrical elements here with these vertical drill rigs, and you can see the shape of the mixing tool looks sort of like an auger, and it's got paddles following the auger section. So these tools right here is cutting into the soil, and we're injecting a grout into the soil, and these paddles are mixing the grout with the existing soil. Here's a photo of mixing next to a building. So you can't see the mixing tool that's buried in the ground right now, but you can see the spoil that's being created as we mix the grout with the existing soil. Get a sense of sort of the consistency of it. It's sort of like a milkshake type of a consistency. There's another view showing the spoil coming out of the column. So one of the things we learn when we do soil mixing is we learn how to get the compressive strength that we want. And that's going to depend on how much cement we use, how much water we use, and what the native soil is. So it's not an exact science, but there is a lot of data out there, published data, and also data that we have as a company. There's some guidance in the form of FHWA, for example, has its design manual here that you see on the right, where they provide design guidance for deep mix columns for embankment and foundation support. There's also a lot of references out there, published references. This is a well-known figure from Taki and Yang that shows you unconfined compressive strength of soil cement with respect to the cement content of the soil cement. So there's a lot of references out there, a lot of guidance for determining your compressive strength and trying to figure out how much grout you need to achieve that. Okay, so I'm going to move on to the next technology, and that is jet grouting. So we borrowed from jet grouting as well. The things we like about jet grouting is jet grouting is sort of proven for it's a proven way of underpinning. It puts soil cement in compression, and it gets installed pretty rapidly. So for those of you not familiar with jet grouting, it has similarities to soil mixing in that we're taking a cement grout and we're mixing it with soil. The difference is we're using a small diameter tool here. This is our drill rod right here. And we're using high pressure grout coming out of this nozzle to erode the soil and create generally a cylindrical element of soil cement. So it's doing the same thing as soil mixing, except it's doing it with hydraulic or erosive energy as compared to mechanical mixing with steel paddles. This is an underpinning job. You can see this is a typical jet grouting drill rig, and we're coming right up on top of a spread footing underneath this column. This is what our tooling look like. Again, it's got this small diameter nozzle on the side. And as we drill down, we come up and we rotate and we create a soil cement column like this here. You can see this column here is about 4 foot in diameter. It'd be a fairly typical column diameter for jet grouting. And here you can see the finished application. So these jet grout columns, these soil cement columns, were loaded in compression from the spread footing, and they carried the foundation load to below subgrade. So these are you can see 3 jet grout columns along the side of this spread footing. And I said one of the things we like about jet grouting is it's a very rapid installation. So this is a log of a jet grout column, and you can see here this particular column, we went about 40 feet deep. It took us 17 minutes to drill and 47 minutes to come out doing our jetting process. So a little over an hour to create this column of about 40 feet deep. So this is a very rapid installation time. And that is one of the advantages of jet grouting. The last technology I want to talk about is this rock and concrete grinding. This is really where the inspiration came for the equipment. So these are very common attachments. You see them throughout the industry for cutting into rock or concrete. You got this generally mounted on an excavator, and there's this rotating drum equipped with teeth that cuts into concrete or rock. Here's an application we're using an attachment to mill away this soil cement here underneath this wall. We're trimming away the hardened material. You can see it piling up here. So these are some well-known attachments in the industry. Okay, so I've given you a summary of those 4 technologies that we've combined. I want to get into the installation here and show you how we actually install a pier using this method. First step is excavating the approach pit adjacent to the excavation. That's similar to how a hand dug pier installation begins. The next step is we're taking this mixing tool, this grinding and cutting tool. We're inserting it into the approach pit. We're starting to inject our fluid grout. And as we're injecting the fluid grout, we're starting to cut underneath the foundation. So that's what we're doing right here. We're doing this cutting and mixing of the soil with grout. We continue that to the desired geometry of our pier. And we stop when we have the geometry we want and when we have the soil cement filled up to within a couple inches of the footing. Next step, this is an optional step, but assuming we're going to be excavating in front of it, we'll oftentimes put a piece of formwork in place to facilitate the removal of this material right here. And then after that, we'll come back the next day and install our dry pack in that gap to give us good contact between the foundation element and the underpinning element. So 6 basic steps, and I'm going to show you some photos later of those case histories, and you'll get a better feel for the equipment and the installation method. Before we do that, though, I want to talk a little bit about design. So thus far, we've been using Soil Mix Pier Underpinning for underpinning structures adjacent to excavations, and that's how I've described the design checks here for you. We're typically looking at these piers either as a gravity type of a pier, gravity wall type of a pier, or externally supported, if needed for, say, sliding or overturning, for example. The soil cement that we're creating has a strength that typically ranges from about 100 to, say, 1,000 psi. Oftentimes, we're operating in about the 300 to 400 psi range is pretty typical, but we can go lower or higher than that. As far as structural design, we're generally looking to ACI 318 for that, and we're following the guidance that they have for lightweight and unreinforced concrete. The unit weight ends up being around 100 pounds a cubic foot, so it's lighter than typical concrete. It's also unreinforced. So there is a stipulation in ACI 318 that for unreinforced concrete for a 2,500 psi minimum strength. However, we do have a lot of experience in using soil cement for compression elements. I gave you an example before of jack grout columns used for underpinning. There's also that FHWA application of soil cement columns for embankment support. So soil cement does get used in compression quite a bit. And our experience has been that if we design according to the ACI 318 guidelines, our soil cement structures have performed satisfactorily for these underpinning applications. So the design of Soil Mix Pier Underpinning, when we're looking at structures adjacent to excavations, we're generally making the following design checks. And it's an iterative process of sorts, of course. So the first step is, we're looking at the existing structure. We're trying to figure out our pier geometry and spacing. We have to make sure that we provide adequate support to the structure from a structural standpoint, but we also need to make sure that our pier geometry is going to achieve, adequate bearing and so forth, adequate depth. So existing structure could be wall footing, spread footing, some kind of combination of that, who knows what's under some of these buildings. It takes test pits, or sometimes you don't really know until you get into the construction what you actually have. If the walls are not in great shape, or if they're like a rubble stone, those are typically going to require continuous support. So after we've looked at that, after we've looked at sort of pier spacing, how many piers are needed, we're going to take a look at the depth of pier and try and figure out how deep we need to go to get to our bearing stratum. And typically we're going to be going at least a foot below the adjacent excavation. That's really a minor bit of embedment there on the excavation side. So we'll neglect that for like sliding calculations, for example, but we will take advantage of it for bearing capacity. And there's certainly conditions arise when the piers have to be extended further than 1 foot below the excavation in order to get to a suitable bearing layer. Then we get into some very traditional wall design, retaining wall design checks, which is sliding and overturning. You're going to have earth pressures on the back of the underpinning, and there's usually a surcharge load as well inside the building, or a level of soil above the top of the underpinning pier. We're going to have a dead weight of the structure that's acting on the pier. This can provide a stabilizing force, so we do need to be careful about when we include that and make sure that that's really there if we're going to be relying on it for anything. And then if we need to provide an external support, we'll do that. External lateral support. Like I said before, that could be a tieback, soil nail, could be a brace. So after we've got sliding and overturning taken care of, we take a look at another traditional retaining wall check, which is checking for compression across the entire base of the pier. We want to make sure that we don't have tension on the bottom of our pier here. And we do that by making sure that the resultant force is within the middle third of the base. Next, we're going to take a look at the bearing capacity. So as part of those calculations before, we're able to then calculate the maximum bearing pressure that we have underneath the underpinning element. Then, of course, we can compare that to an allowable bearing pressure that we have for that soil layer. After the geotechnical design is satisfied, we're going to take a look at the soil cement itself and figure out what sort of compressive strength we need. We're generally going to have axial compression, we're going to have bearing stress, and we might have some shear forces on the pier. So axial compression, this is resultant, of course, from the weight of the structure, the self-weight of the pier. We might have a post-tension tieback that's angled down, so there's going to be potentially vertical load from that external support. We're going to have some one-way shear from our earth and surcharge loads, and definitely we'll have shear if we have an external support coming through the side of the pier. And then as far as maximum bearing stress, we're generally taking a look at the bottom of the footing and the top of the pier to make sure that we're covered there for bearing stresses on the soil cement. And last but not least, this is a very important check, estimating settlement. We're trying to support this building. We're trying to keep it from moving. We do not want a lot of settlement. So it's very important to check to perform an estimate of settlement if the pier is not going to be bearing on rock or similar very hard stratum. Of course, there's a lot of ways to estimate settlement. You can look at it from a few different ways. It's settlement estimates are just that, they're estimates. So it always pays to look at it a few different ways, make some different estimates, and then we want to compare these to our performance requirements that we have for the underpinning, and make sure that that we're confident that our piers are going to perform as needed. So it's an iterative process. If anything here is inadequate, you're going to go back and revisit geometry, spacing, depth, that kind of stuff, and repeat the calculations. Okay, I want to talk a little bit about QA/QC. So this is a construction process. We're trying to make sure we're doing a good job on the field and we're installing these things the way they're supposed to be installed. So these are some fairly basic QA/QC measures that are followed during the installation. So first off, of course, is maintaining a daily log of the pier installation, keeping track of where we've been, how deep we've gone, how much grout we used, that sort of thing, what the grout water cement ratio was. The installation can be a pretty productive method, and so it is important to keep track of where you've been. We want to avoid undermining too much of the structure at any one time. Second, as we look at the grout production, there's several things there that we want to maintain logs of. So we want to keep track of how many batches we've made of grout, how much cement we've used, what sort of grout water cement ratio we've been producing. We will measure the specific gravity of the grout to confirm that we are getting the correct water cement ratio in our batches. Another thing we do is we collect wet grab samples of the soil cement, and then we're going to perform compression testing on those. So here you see some typical 3x6 cylinder molds. We're going to be collecting, typically about 4 cylinders a shift, and then performing compression testing at various time intervals to confirm that we have the right grout mix and we're achieving the compressive strength that we need. I'm going to take you now into some project histories, show you some photos, and give you a better idea of where soil mix piers have been used in the past. This was a neat project here, the first project, 2100 L Street. This was a job in Washington, D.C. This is a very complicated job. Soil mix piers were just a part of the job, but they did serve an important role. As you can see here, there's a lot going on. I have put a yellow ellipse around the soil mix piers that were installed. We performed soil mix pier underpinning beneath this existing brick foundation of this building. We did it along here, and we did it along here. This is where the depth limitation for soil mix piers applies. There's no way to install these piers. In this case, we're going 35 feet or something like that. There's no way to do that in a single pass. And so for this project, we elected to install soil mix piers immediately underneath the foundation to stabilize the foundation. And then we installed hand dug piers beneath that to support the soil mix pier underpinning. So here you can see the tool being attached to the excavator. This is a photo of the typical excavator machine working next to the building. You can see there's just been a small amount of excavation so far. So we've excavated an approach pit. We've got our tool down there, and we have a grout line running to the mixing tool. This is a view down into the approach pit. We're starting to cut into the soil, mix it with grout. Just looks like sort of a mess down there right now. The mixing is progressing. You can see this nice rich gray color, which is all of our cement. being mixed into the soil. So this is the beginnings of the soil cement being created. And here you can see we're getting farther and farther up. Here the soil cement level is down here. Now we're coming up very close to the foundation. The mixing tool is submerged. When we're all done, it looks like a big mess, but it's soil cement here and also underneath the foundation. And you can see this is the brick foundation. It was an okay shape. It was in decent shape. Not terrible, but not great shape. This is the sort of the finished product at this stage. So you can see here the smooth surface is from the bond breaker that we put in, but we have soil cement from the top here down. There was some sort of rubble, concrete stuff underneath the bricks in some cases, some places more than others. But this is soil cement right here, continuous soil cement left to right. This was a heavy building. We had about 20 kips a linear foot of wall load on this exterior wall. And then zooming out again, this is the photo I showed you before, just to put it in context. This right here, this wall right here is this right here. So that was a neat project. The Soil Mix Piers performed a really important role there. There's a question here about material segregating out of the soil cement. We do see that sometimes. That will happen sometimes with the more granular soils, if there's not enough fines content in the soil. So we'll take measures either with admixtures or sometimes adding a clay product to the soil that helps with material segregation, keeps everything in suspension and prevents the settling out of the larger particles. But generally, the soil cement, there's not a lot of segregation that occurs in the soil cement.
Hey, Matt, there was a question too right before that, a little one up.
Oh yeah, okay. Yeah, this was a question about sequence. Yeah, correct. Yeah, there's definitely a sequence installation. So we're going to look at spacing. We're going to look at spacing these piers out. So for example, if we did this pier on Monday, we would look at doing, say, this pier on Monday and this pier over here on Monday. We would then come back on Tuesday, dry pack, and at that point, we could come in between and install this pier here. But this is a short section of wall, so this would take us several days to sequence that because we don't want to undermine too much at one time. Typically, we're not going any wider than about 5 feet at a time, and we're skipping over at least 15 feet clear space in between our piers. So there is a lot of sequencing that happens on the project. We want to make sure we don't undermine too much of the building at any one time. Okay. I'm going to show you the next history here. This was a project on New York Avenue in DC. This is a brick wall that needed to be underpinned. There was going to be an excavation here adjacent to it. So you can see that sort of typical construction sequence. We've got a approach pit excavated next to the existing foundation. This is the mixing in progress. It's messy looking, but this is soil cement. You can see the gray color there. This pier is just about done. You can see it's very close to the bottom of the foundation. This was an interesting project because we installed 2 tiers of soil mix piers. So the excavation went about 20 feet deep in sections. So we went and did an initial tier of soil cement, soil mix piers, and then we excavated and came down and dug an approach pit and got in here and installed a second tier of underpinning. So this from here to here was the first lift of Soil Mix Pier Underpinning. And now in this photo on the right, we're installing the second lift. This plywood is simply put up to serve as a backer board for the waterproofing membrane. Here's a photo of that second tier of Soil Mix piers being installed. You can see the teeth marks. This is the hardened soil cement from the first lift. And this was the finished product. Again, this is just for the waterproofing membrane. You can see we use soil nails to provide lateral support to this excavation wall here of soil cement piers. Here's another project, the third project I want to show you. This is a project we did up in Boston. We are working next to this building here, future excavation. You can see they've excavated the site down, and now we're underpinning this building here. You can see an approach pit is dug here. The building is not real substantial, but it needed underpinning. So here you can see the excavator working next to the building. You see the grout line going to the excavator. There's the soil cement coming up. You can see we've gotten underneath the foundation. And then that is the finished product here. You can see this. This is the existing basement wall, and this is the exposed soil cement with a few nails through it for some lateral support. If we do multi-tiered walls, yes, we would dry pack in between lifts to make sure we have good contact there. And then as far as putting soil nails through, requiring any reinforcement of the soil cement mix, no, we are designing the soil cement just as plain unreinforced soil cement. And so we design, the piers are generally relatively thick, say compared to a soil nail wall facing. The piers are generally, say, 3 to 4 feet thick. And so we design for punching shear, one-way shear, those sorts of things. Normally, the soil nails are spaced closely enough that bending is not a concern. So we're just designing them as unreinforced piers. You could put a shotcrete facing over the face of it, though, if need be. That would definitely be an option. So these bearing plates here could be with headed studs, for example, and you could put a permanent shotcrete facing over the face. Another question, do you use steel wedges to transfer the load? No, we typically do not. We haven't done that before. To transfer load between the footing and the soil mix pier, we simply use dry packing. So I want to summarize for you the things that we've gone over here. You know, I think everybody knows what underpinning is now, hopefully. Hand dug piers have a long history. We developed Soil Mix Pier Underpinning really to get away from that manual labor. You know, hand dug piers can be done safely, but bottom line is there's a lot of labor involved, and anytime you can reduce labor, you can reduce accidents. So when you look at the design, you've got the geotechnical and structural components to look at. You know, this is a material that's you know, generally about a tenth of the strength of concrete, 100 to 1,000 psi. There's QA QC we can do during construction, and you know, you can see we've underpinned a variety of structures so far. And so you know, just really my closing remark I want to make is that we see Soil Mix piers as a good replacement for hand dug piers. We like the fact that performance is very similar to hand dug piers, and we've improved upon safety, cost, and schedule. So it's a win all around.
All right. Well, thank you so much to Matt for a really interesting presentation here. We got one more question at the bottom as far as the cost comparison versus hand dug pits. How would you answer that, Matt?
I would say we can generally beat hand dug piers on cost. Yeah, we can. Time is money. We can install the Soil Mix piers faster than we can install hand dug piers. So it can be cheaper for us to install, and it's cheaper for the general contractor or owner because we can accelerate their schedule as well.
I see some questions around specifications. What we can do is we can have Matt follow up with everybody, maybe send an email out with some information on the system or any specs or information that they have. This way you all have it, and you can then obviously get right in touch directly with Matt if you have additional further questions, if that works for you, Matt.
Yep, that'd be great.
Okay, great. All right, so we'll make sure that that happens. I want to thank all of you for joining us today. Again, I want to thank Matt for a great presentation, and I want to thank Schnabel for sponsoring EMI's content. We have a platform of 7 podcasts, 3 YouTube channels. All the content, including these webinars, are free for engineering professionals because of sponsors like Schnabel, so we really appreciate it. The evaluation is in the chat. You have to complete that to get a PDH, but even if you don't need a PDH, we'd love to hear from you. Give us a couple of weeks to process your PDH, and then you'll receive it. And when you respond to the evaluation, put some notes in there if you like additional topics. If there are specific things you want to hear more about. We can definitely talk to Schnabel about doing some more webinars in the future, but we want to definitely meet the needs and kind of what you need in your career around these items. So thanks again to Schnabel. Thank you, Matt, so much once again. And thank you all of you for your interaction today. Lots of great stuff in the chat. We will see you on our next EMI webinar. Thank you, everyone.